In this video, we're going to do a couple examples of tension problems together to help you understand the concepts from the reading and how to apply them. In each of the following pictures, we have a collection of blocks hanging from strings. There are also hanging scales drawn as empty circles. Let's assume that each of the scales have no mass. All of the blocks are identical and have a mass of 1 kilogram. The strings and pulleys are also massless. Write in the value in newtons that you would expect to see on each scale inside each circle. So the first scale is hanging all by itself and not supporting a block, so this scale says 0. The second picture has a single scale holding up a single block. A 1 kilogram block would weigh 10 newtons. The third scenario has two scales, each sharing the load of holding up a 1 kilogram block. So each scale would say 5 newtons. Our fourth scenario has a scale holding up a block, but as the string is cut with scissors, the scale isn't holding up the block anymore, so the scale will say 0. In the fifth scenario, we have two blocks hanging from two scales. It's sort of like a vertical train. The bottom scale is only holding up the bottom block, so it says 10 newtons. The top scale is holding up both blocks, so it says 20 newtons. Our last scenario has a block hanging from two scales. The first scale is vertical, and the second one is attached to the wall after a pulley. The vertical scale is going to say 10 newtons because it's holding up the whole block. The second scale also says 10 newtons because it again is holding up the block. All the pulley does is change the direction of the force, not the amount of force involved. A common test of strength involves holding up a phone book by two strings. If the strings are vertical, it is not hard at all. Each string just has to hold up half the weight of the book. We can show this formally. We can say that the sum of the forces in the y direction is 0. Going upward, we have two tensions, Ft and Ft. Going down, we have the weight, Fw. We can combine like terms and say 2Ft equals Fw. If I get Ft by itself, it is equal to Fw over 2, which is half the weight, just like we said. It becomes a contest when you ask that the strings be held as horizontal as possible. Look at this free body diagram. What would happen if the tension in each string was simply half of the weight of the book? The book would fall down. Let's look at a few pictures that illustrate why this is hard. If we want to hold the two strings at a modest angle, we don't have to pull very hard for each string to be holding half the weight. If we want to be at a lower angle to get the vertical sides to be half the weight, we have to pull a lot harder. If we go to an extremely shallow angle, in order to get half the weight held up in each string, we have to pull ridiculously hard. No matter what we do, we can't get the strings horizontal. It's not a question of strength. If Superman played this game, he couldn't get them horizontal either. But he would be able to pull so hard that the strings would actually snap before they got to 0 degrees. What is the limit to how horizontal the strings can get? Is it possible to win this contest? The vertical components of each string must always hold up half the book. As the angle gets lower and lower, the tension along the diagonal must get very high. It is not possible to get the strings to be horizontal. I want to hang a very important sign from two strings as shown here. The left string is perfectly horizontal, and the right string is making a 30-degree angle with the sign. What is the tension in each of the ropes? Okay, we're going to start with a free body diagram. So this dot represents the hanging sign. We know that the sign has a weight, which I'll draw going downward, and we know it has a tension off to the left, which I'll call FTA, and it has a tension up and to the right, which we'll call FTB. These three vectors have to add up to 0, and to see that better, I'm going to draw the x and y pieces of FTB. There's a horizontal piece of FTB going to the right, and there's a vertical piece of FTB going straight up. Now that my diagram is all set, I'm going to do two math problems, one in the vertical direction and one in the horizontal direction. I'm going to start in the vertical direction. The sum of the forces in the y direction equals 0. So the upward force equals the downward force. FTBY equals FW. I can rewrite FTBY better as FTB sine 30 degrees. And FW I can write better as G times M. I can now substitute in some values. The sine of 30 degrees is 0.5, and FTB still goes here. And on the other side, the gravitational field strength of 10 newtons per kilogram times 100 kilograms means the sine weighs 1,000 newtons. So this gives me a value for FTB of 2,000 newtons. Let's switch to the x direction. The sum of the forces in the x direction is 0. All of FTA is going left, and just the x component of FTB is going right. So I have FTA on the left equals FTB times the cosine of 30 degrees. So FTA equals the full amount of FTB, which is 2,000 newtons, times the cosine of 30 degrees. Let's see, in my calculator, the cosine of 30 degrees is 86%, so FTA is 86% of 2,000 newtons, which is 1,700 newtons. Notice, there were two things to solve for in this problem, FTA and FTB. Since I'm using algebra, I need two equations to solve for two unknowns. I got the two equations from the two different directions in the free body diagram. Mom wants to hang a giant rubber duck piñata from two angled ropes. What is the tension in each of the ropes? The mass of the duck is 25 kilograms. This dot represents the duck. The duck has a weight, which I will draw downward. It has the string A pulling up and to the left, which I will label as FTA. It has string B pulling up and to the right, which I will label FTB. There's two things to solve for, so again, I'm going to need two equations. I'm going to do my math in the y direction and in the x direction. I'll start with the y direction. The sum of the forces in the y direction equals 0. That means that the weight going down is equal to the y component of FTA plus the y component of FTB. I can rewrite that as FW equals FTA sine 60 degrees plus FTB sine 40 degrees. The weight of a 25 kilogram duck is 250 newtons. The sine of 60 degrees is 86%, so I'm going to have 86% of FTA pulling up, and the sine of 40 degrees is 64%, so that means 64% of FTB is pulling up. So now I've got 250 newtons equals 86% of FTA plus 64% of FTB, and I'm stuck. I can't solve anymore. I don't know what A or B FTA or FTB are. So instead of giving up, let's just go over to the x direction. The sum of the forces in the x direction is 0. That means that the x component of FTA is equal to the x component of FTB. So I can rewrite FTA x as FTA cosine 60 degrees, and I can rewrite FTBx as FTB cosine 40 degrees. Cosine of 60 degrees is half, so half of FTA equals the cosine of 40 degrees is 76%, so I've got 76% of FTB on the other side. I can get FTA by itself by dividing the 0.5 over to the other side, and this tells me that FTA equals 1.52 times FTB. I'm stuck again, but I can now use this and go back to the other side. I can say that 250 newtons in the y direction equals 86% of 1.52 FTB plus 64% of FTB. So 86% of 1.52 is 1.3. So I've got 1.3 FTBs plus 0.64 FTBs. Okay, so 250 newtons is equal to 1.94 FTBs. That means FTB by itself is 130 newtons. Now, I'm not done. I don't know what FTA is still, so I can go back to the other side and put in what I know. I know that FTA is 1.52 times FTB. So 1.52 times 130 newtons is 200 newtons. And I have both answers now.